Hello scholars, welcome. Mr. Hinkle here. We're talking about the interrelation of the atmosphere and the oceans. And in order to get an understanding of this relationship, let's talk about the atmosphere specifically for a moment. So this is the atmosphere introduced. And our objective in this lecture is to introduce the atmosphere, fitting I know, describing the composition, layering, pressure, and movement of air, because air, wind, drives ocean circulation. So let's get into it. The atmosphere, vital part of Earth. It's a thin layer of gases that envelops the entire planet. It plays a crucial role. Why is the atmosphere important? Well, the atmosphere supports life. It regulates climate, and it protects Earth from harmful radiation. Wow, all that in the stuff that's surrounding me that I can't even see. Amazing, right? I know. Let's keep going. So what is air? What the heck is air? Mostly nitrogen, oxygen, yes. I think we know that we need oxygen to breathe. That makes up about 99%, right? 78 and 21. You add those together, 99% of oxygen of the atmosphere of air is nitrogen and oxygen, which means that about less than 1% is other gases. Now, these other gases play a very important role. Within this, we've got a lot of argon, neon, methane, ozone, water vapor, carbon dioxide. Carbon dioxide is such a powerful greenhouse gas because of its ability to absorb and re-emit heat, accounts for only 0.04%. That's why such small impacts to this value have large effects on our global climate. But more of that when we talk about climate change. Right now we're really looking at what is air and how does air move in the atmosphere. So now that we know air is mostly nitrogen with some oxygen, less than 1% gases, air has a structure. Surprise, surprise. And the structure of the atmosphere is pretty cool. We've got the troposphere where all weather happens. Basically, temperature decreases as you go higher. That's why mountains have snow on top of them, and sea level rarely, and at low latitudes, never does. Then we move up into the stratosphere, where what happens here is you have now temperature increases with altitude, and then the mesosphere temperature decreases again significantly. This is where meteors start to burn up, and then the thermosphere temperature rises again. If you've ever heard of the Northern Lights or the Aurora Borealis, this is the part of the atmosphere where this is occurring. And then we move out into Earth's outer atmosphere, the low gravity orbit. This is where spaceships, the space station, and satellites will orbit the Earth about 600 kilometers above Earth's surface. So the troposphere, stratosphere, mesosphere, thermosphere, and exosphere are the 5 distinct layers of Earth's atmosphere. And their boundaries are where you have changes in the direction of temperature. High to low to high, high to low to high, out into deep space. So let's zoom in on atmospheric pressure. The pressure at sea level is 1 atm. We'll call this sea level here. If we remember from ocean pressure, every 10 meters is 1 atm. So that means at 2 meters depth, the pressure in the ocean is 3 atm. It would be 2, so 2 meters is 20 meters. That would be 2 ATMs plus the 1 ATM for 3 ATMs. It's always the depth plus 1. 20 meters. Let's make sure I get my math correct here. At 20 meters depth, 3 ATMs. And that is because the deeper you go, the more water you feel pressing down on that specific location. So this is how water pressure works. Air pressure is exactly the same. At sea level, you feel the weight because air has mass and weight. Nitrogen, oxygen are elements that have mass and weight. So at sea level, you feel the weight of all the overlying air above it. The higher you go, the less air to press down. Which is why, if you've ever been at high elevation, you find it hard to breathe. Because what's happening is there's less oxygen available because less air is being pressed down, meaning there is a lower air pressure. And with lower air pressure, there's less molecules inhabiting that space, meaning you find it hard to breathe. So air, the air column, similar to the water column. Air pressure and water pressure are similar in that at the bottom you feel the weight of all of the material, all of the mass that's overlying. Okay, so high pressure and low pressure. Interesting. Got it. High pressure and low pressure. Well, we're going to get into a discussion now about movement of the atmosphere. And the atmosphere is always moving from high pressure to low pressure. And in order to display this, I've got a balloon. The handy dandy balloon of science. So, the air inside is being squeezed by the balloon. I'm blocking the top of it off here, but the pressure inside is higher than the pressure outside. When I release it, that air that's being squeezed moves out to the surrounding area. Wind always blows from high pressure to low pressure. And so what we have is high pressure where molecules are densely packed together, and low pressure, we can have differences in pressure at Earth's surface because of differential heating. Heat causes molecules to spread apart. Hot air rises, this is a thing. So we've got high pressure, here's Earth's surface, that moves to low pressure. That low pressure is hot, and so it rises. Now, this warm air that rises is going to make its way over to this cool air, and then cool air sinks. Cool air sinks. Warm air rises. I think we know this just from growing up. We're like, yeah, it's warmer in the top, the warm air rises. So this movement of high pressure to low pressure Earth's surface, hot, warm air rising, cool air sinking, this creates what's known as a convection cycle. So, or convection cell, convection cycle, convection pattern, but let's just stick with what we got up here. So this is an idealized model of how air moves. The sun heats the Earth unevenly. That uneven distribution of heat creates areas of high pressure and low pressure. Earth's surface, air moves, wind blows from high to low pressure. Low pressure warm air will rise, high pressure cool air will sink, creating a convection cell. So how does this apply to the Earth? Well, it's warm at the equator, it's cold at the poles. So in an idealized version, we would have this basically from the equator to the pole, where the poles are cold, cool air would sink, and then high pressure would move all the way over to the equator, where warm air would rise because it's hot, and lower pressure and then it would form this single convection cell. But this is not how the Earth works, because there is a caveat to what's happening. What's going on? What could interfere? What could get in the way? Any guesses? The Earth spins. The Earth rotates every single day. Again, the sun comes up. It's so dependable. I've never woke up and not seen the sun. But because the Earth rotates, what ends up happening is from 0 to 30 degrees, you get a convection cell. From 30 to 60 degrees, you get another convection cell. And then from 60 to 90 degrees, you get yet another convection cell. So the northern hemisphere and the southern hemisphere have 3 distinct convection cells. Here, 60 degrees, 30 degrees, equator, 30 degrees, 60 degrees. Here's 90 at the top and at the bottom. So I'm going to take a little time right now to show this. Hot air at the equator. Hot air rises. So the equator is going to heat up, and it's going to rise. Now, this air is going to move towards 30 degrees, where it's going to be very cool, and sink. Let me do more arrows. Hot air rises. It moves away from the equator, and it sinks at 30 degrees. Here it's high pressure. High pressure moves to low pressure. High pressure moves to low pressure. So there we have just built our Hadley cells. Well, if it's descending here, high pressure to low pressure is going to happen from 30 to 60. Then air is going to rise, finishing that cell. Same thing is happening here. Descending air at 30 degrees, high pressure to low pressure, rising air, filling that space. There we have our Ferrel cells. And then one more. And we said that air was going to descend at the poles. That definitely happens, giving us our polar cells. Air rises at 60, descends at 90, high pressure to low pressure. So let's use this one right here. We've got Hadley, Ferrel, and polar. The Coriolis effect is another video. Please check out that video. I'm not going to explain it in this one, but the reason that we have 3 distinct convection cells in Earth's atmosphere is because of the Coriolis effect. What these convection cells do, let me verify, yep, okay, is create preferred wind directions. At the equator, we've got the trade winds. At the mid-latitudes, we've got the westerlies, and then up near the poles, we've got the easterlies. Prevailing wind patterns. Now, the Earth is complex and it's nuanced, so it doesn't always stick to this, but due to the unequal heating of the Earth and the rotation creating a force known as the Coriolis effect, we get 3 distinct convection cells, giving us prevailing wind patterns in the atmosphere. So this is a really cool topic. It's kind of something you got to think about for a little bit, maybe draw on here, but let's do key points. Unequal heating from sun. Look at my video on seasons. That's in this module also. 2, rotation of Earth. This gives us the Coriolis effect, so this is the review. The Coriolis effect. 3, we have wind in convection cells. There's 3 of them, as we've seen here. that gives us prevailing wind patterns. And if I may, connect prevailing wind patterns to ocean circulation, because wind is the primary driver of surface currents, then we have yet again another connection between the atmosphere and the ocean, but now we're getting a little bit deeper into the subject. So thank you so much, and I'll see you again in the next one.